So just a quick recap about what we did in the previous class. So I defined a very general notion of an optimization problem, or at least a class of optimization problems that we're interested in. Right? We saw that the class that we're interested in is the following. So we want to solve x star, which is equal to the argmin of some function f of x. F could be any general function. And we have a set of constraints which can be specified as some g of x is less than or equal to 0. Right? And we saw that at least several different types of problems can be modeled in the same way, in this particular way. In particular, a maximization problem can be cast in the following general form. And different kinds of inequality constraints can also be set up in this particular form. Of course, it's not fully general. In particular, we saw that if we have a constraint which is strict, such as g of x should be strictly less than 0, that cannot be posed in this general form. Right? And there's a reason. So we'll formally define why that is the case a little later on. But generally speaking, the reason why we are doing this is because if we have strict inequality constraints, then the set of inequalities or the constraint set is no longer closed, and therefore you cannot guarantee the existence of a unique minimum or a maximum, even the existence of a maximum or a minimum, right? But on the other hand, if the constraint set, it turns out, if it is closed and it is bounded, then irrespective of what the function is, as long as it is continuous, you can always guarantee the existence of a minimum as well as a maximum. Okay, but we'll see this as we go along. So we saw a bunch of examples. First, we saw the least square solution for a system of linear equations. So given ax equal to b, where A is a fat matrix, this may not have a unique solution, so we can instead try to find that vector x which at least approximately satisfies this particular equation. And approximately satisfies was in the sense of minimizing the squared error between ax and b, right? And that gave you the solution turned out to be the pseudo inverse times the vector p, right? And you can add additional constraints. For example, you can add L2 norm constraints or L1 norm constraints, or depending on the application that you have, these constraints give you what is called a constrained least squares problem. Now, these are generally nice problems. In the first case, we saw that we have a closed form solution for this problem, right? But then once you impose constraints, you may no longer have a closed form solution, but you could still find it efficiently. We then saw a slightly different problem, that is, you have a communication system, you have a total power budget, and your goal is to divide this power among these different channels, so to speak, so as to maximize the rate. And again, it doesn't matter if you've not seen this before, or if you're not familiar with communication systems, but you can take it for granted that the total rate that you can achieve in the communication system is given by this expression over here, where the sigma I squares are given to you, and your goal is to subdivide this p, power p, allocate it across the different channels. Pi is the amount of power that you're allocating to the ith sub-channel. This will be the total rate that you can achieve, and your goal is to allocate the power so as to maximize this particular expression. Right? This comes up very frequently in wireless communications. And it turns out that the optimal solution is not to just put all the power into the best sub-channel. If your goal is to maximize the rate, it turns out that there's a different solution. Again, you can evaluate this. It's this is another problem which can be solved very efficiently. It turns out to be a nice convex optimization problem, and can be solved efficiently. So now, again, before we proceed to another couple of examples, are there any questions from the last class? Any questions? Okay, so let's look at another example. And this is from machine learning. All right, so this is a classic problem in machine learning called empirical risk minimization. So think of a common learning task. For example, you want to estimate something, or you want to predict some particular quantity. For example, let's say maybe you want to predict whether there is a particular object in an image. Right, that's a common object detection task that arises in machine learning. So how do you even set up this particular problem? How do you formulate this problem and how do you solve it? Our goal is to somehow design a system that predicts whether this maybe a cat is present in an image or not. Right? Again, you can't really fit a particular model for this kind of data. How do you predict the presence of cats? Right? So then what do you do? What we can do, what we have at our disposal is a whole bunch of pictures which we know have cats, and a whole bunch of pictures which we know they don't have cats. They maybe have dogs or something else. Right? So given this vast amount of data, our goal is to somehow design a system which can predict, if you see a new picture, it has to predict whether it contains a cat or not. Right? So what do you do? So what are we given? So we're given a bunch of images, or basically we have labeled data set. So what are we given? We're given a labeled data, which, I mean, one way, for a concrete example, it's a collection of images, each of which have a label. Cat is present, cat is not present. Okay, and that corresponds to the truth. Okay, you know that this label is that this data is fully sanitized. Okay, but now our goal is to design a predictor, right? So how do we model this predictor, and how do we sort of set up this particular system? So one way that we go about this is we assume that there is a ground truth. Okay, so, and how do you model the ground truth? So we'll assume that the ground truth is some function. Okay, some function which takes as input an image and outputs whether there is a cat or there is no cat, 0 or 1. So it's a function which takes as input the set of all possible images of maybe a particular size, and it outputs either 0 or 1. So 0 means no cat, and 1 if there is a cat. Okay, this is the ground truth. We don't know what this is, but we can assume that there is a function which does this. Our goal is to somehow learn this function, right? That's what a lot of machine learning problems try to do. Okay, so far so good. Any questions? Okay, so our goal is to somehow learn this function, but I mean, the space of this function is pretty huge, right? You can't possibly learn it with just a small set of images, right? If you really had to learn this function fully, then the only way to do it would be you take all possible images in the universe, tell me the output, and that's the only way you can learn this function exactly. So the question is, can we approximate this function somehow given the data that we have? Okay, so we're given the data. So how do we model the data? The data is basically a set of pairs, image 1 and its corresponding label, L1, image 2, the corresponding label, and so on, right? Maybe I have M images and the corresponding M labels. Okay. So remember, our goal is to approximate this particular function, right? So instead of looking at the class of all possible functions, maybe I'll restrict myself to a subclass of functions, and I'll try to approximate this function from this unknown function from my class, right? So I'll take a subclass of functions. All right. So for example, I could think of the set of all possible linear functions from the images to 0 or 1. A set of all linear functions whose input is an image, the output is maybe a real number. Okay, that's one way to think about it. Or it could be a slightly wider class. You could think of set of all polynomials of a certain degree, or what is more commonly used, set of all possible neural networks, right? Of certain parameter sizes with certain hyperparameters, right? So there are certain parameters that we can choose in these functions. So for example, if I take linear functions, then what is a linear function? A linear function can be represented in terms of a matrix. So the entries of the matrix would be the parameters that we can vary, right? If you take a polynomial, then the coefficients of the polynomial are parameters that we can tweak. If you take a neural network, then essentially the weights of the neural network are parameters that we can tweak. So these are going to be our optimization variables finally. Right, so maybe I have n parameters, n real valued parameters that I can choose any way I want. So for example, it could be a neural network with n weights, it could be a matrix with n entries, or it could be a polynomial with n coefficients. Okay, and so the problem is basically I have this subclass of functions. My goal is to find that function from this subclass which best approximates the ground truth. Right? So it's basically, you can think of it as a curve fitting problem. But unfortunately, we don't have access to the function itself. Right? All we are given is a set of points, right? Or a set of images. That's our data. Correct? So actually, what do we have? We have a bunch of points, I1, I2, I3 up to IM, and L1, L2 up to LM, the labels, are essentially just evaluations of this function at those points. Right? That's one way to think about this particular setting. Right? There's a ground truth. What we're given is data, of course. Now there's an underlying function which I call the ground truth, and the data can be thought of as just evaluations of this ground truth function at a bunch of points. My goal is to, given these points, so if you think of it in, say, one dimension, you're given a bunch of points, that is x, y values. And basically a predictor is essentially just a real valued function in this toy example. And the goal is to find out, let's say if I want to approximate it by a linear function or an affine function, then what is that function from this particular class which best approximates my data? Correct? That's the problem that we're trying to solve. Okay, so of course, so now we know what our optimization variables are, right? We're choosing a class of functions, and the free parameters are basically the variables that we can optimize over. Now we need an objective function, correct? So how do we define our objective function? Our goal is to somehow choose that function which best approximates the data we have. All right. So one way to do it is we want to minimize sort of the number of errors. Correct? We want to make sure that our goal is ultimately to design a predictor, remember. So we want to minimize the number of maybe mispredictions, correct, or wrong predictions. So the standard way to do this is to define what is called a loss function. So suppose that the true label is L and I predict something else. Then how bad is it? That's measured using a loss function. So have a loss function which takes, say, one label. In this particular example, let's assume that we're looking at functions whose output is always either 0 or 1. Okay. So to some are greater than or equal to 0. Okay. So it's L of say L1 comma L2. So these are the predictions, the predicted. So one of them is the true label, the other is the predicted label. If the true label is L1 and I predict it as some other L2, then how much loss do I incur? Right? Again, depending on the application, you may want to choose a different loss function for the same kind of problem. Right? So one very simple loss function is to count 1 if you make an error, if you say 0 instead of 1, and 0 otherwise. Right? So you look at the 0, 1 loss, which is L of say L comma L prime. So it is 1 if you predict wrongly, and 0 otherwise if you predict it correctly. Correct? And my objective function that I'm going to take is going to be the following. So my g of alpha is going to be, I want to minimize the sort of average loss. Okay, so I have m points, right? I have m data points. Out of these, I want to know what is the average loss. The average loss is going to be 1 up to m L of Li. So what is the true label? The loss between the true label and what my prediction is, which is f alpha of I. Right? So this is the image which is given, which is presented to the predictor. The output of the predictor itself is some function, right? And f alpha of I is going to be the predicted value. The true label is Li, and the loss for the ith data sample is going to be this particular quantity. Right? And this basically counts this basically accumulates all the losses and averages it out. So this is the average loss that you would incur over this particular data set. Correct? This is for a given predictor, right? And ultimately, what would be the goal? The goal would be to minimize this particular quantity. So this quantity on the right is typically called the empirical risk. Right? So the standard problem in deep learning is to design some kind of an algorithm which minimizes the empirical risk, and the minimization is typically taken over the parameters alpha, which are typically the weights of a, say, deep neural network. Correct? So the optimization problem in this case is the following: compute alpha star, which is argmin overall possible alpha of g of r, right? Now, unlike the previous problems, this is a lot more complicated to solve, right? So we're not guaranteed that this objective function is convex. Remember, so if you take a look at this particular quantity, this is essentially a sum of m functions, right? Which could be like really complicated. And you're minimizing over possibly a huge number of parameters. right? So these machine learning problems have, say, thousands or millions of parameters. So that's the optimization variables. So you'll have millions of optimization variables. The function that you're trying to minimize could be really, really complicated. It could not be smooth. It need not be smooth. It could potentially be, it almost always is non-convex. So the goal is in machine learning typically is to design algorithms to solve this optimization problem. Right? And a lot of the techniques used over there build on optimization tools developed for convex functions. Right? Even though the function of interest is not convex, you can still try to use ideas from these to get at least an approximately good solution for this particular problem. Right? Any questions? Okay, so let's look at one last example. And this is the problem from computer science. All right. So it arises in a number of other areas, such as networks. And the problem is as follows. So suppose I give you a graph, right? You're all familiar with what a graph is. Hopefully, you have a collection of vertices which are connected by edges. Right, and given a graph, there are several parameters of interest, right? And there are many different ways of specifying a graph. Of course, there is this pictorial representation, but an easier way is using what is called the adjacency matrix. So right, so if I have a graph on n vertices, then the adjacency matrix, let's call it A, is an n by n matrix where the I comma jth entry is equal to 1 if the vertex I is connected to vertex j, and it's equal to 0 otherwise. Right, so just to understand things, let's take, say, this particular graph. I label them 1, 2, 3, 4. So the adjacency matrix would be a 4 by 4 matrix. And where would the non-zero entries be? Yeah, so this is first row, second column, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1. Yeah. So any interesting property about this matrix that you can see? It's always going to be a symmetric matrix, right? Because as long as you have an undirected graph, this is an example of an undirected graph. If vertex I is connected to vertex j, then j is obviously connected to vertex I, right? Okay, so given this particular graph, one common problem is to find out what is the maximum number of edges crossing over from one subset to another subset, right? So let us say I take this given graph and partition it into two subsets of vertices. Okay, so maybe I take vertex 1 and 4 on one side and vertices 2 and 3 on another side. Okay, and I try to find the total number of edges which cross over from this set to this particular set. So graphs can be used to model several different things. In fact, graphs can be used to model circuits. Graphs can also be used to model communication networks. Right? So given two sets of vertices, what is the number of edges crossing over? Okay, so given any graph G, and any partition of the vertices So suppose I just take the set of vertices, I split it into two sets, V1 and V2, which completely exhaust all of V. The number of edges going from V1 to V2 is said to be a cut, or the size of the cut. Right? So any partition into two vertices is called a cut, and the number of edges crossing over from one side to the other is called the size of this cut. So for example, if I take this particular graph over here, and I take the cut 1, 4 on one side and 2, 3 on the other side, what is the size of this cut? It's 3. Right? If I take 1, 2 on one side and 4, 3 on the other side, what is the size of the cut? 1. So in many problems, you want to find what is the size of the maximum cut. Right? So for this graph, what is the size of the maximum cut? It's 3, right? Basically all the edges. Okay. The max cut,
set will always be 2.
which one?
V1, V2.
Yes, it's always, typically you always take only two. Yes, two groups. That's a partition of a graph G is the size of the maximum cut, the size of the largest cut. Right? Well, I've described this verbally to you, but after all, if we want to solve an optimization problem, right? So this is, as you can see, it's an optimization problem, right? There are different cuts, and you want to find what is the maximum cut. So can we come up with an expression for the max cut? Right? Or basically, what is the objective function? What are the variables? Okay, so first, even before putting things on paper, what is our variable? Yeah, so sets in some sense, right? So basically the partition, you can take different partitions, and one way to, I mean, there are different representations that one can say. Basically, if you take a collection of vertices on the left, then the collection of vertices on the right is automatically fixed. Right, so we can say that, okay, I'm going to take a collection of vertices, and that is going to be what I can optimize over. Right? That's going to be the variable that I can change. Okay, so we need optimization variable. Okay, which is going to be some subset V1, which is a subset of all the vertices V. Okay, I'm going to write this in a slightly more convenient fashion in the form of a vector, which is going to be the following. So I'll take the vector x, which can take values either +1 or -1. Okay, +1 comma -1 raised to the n. So +1 indicates that it's a vertex on the left. -1 says that it's a vertex on the right. Okay, it's just a labeling, right? After all, I have n vertices. I can order them in any fashion I want, and +1 indicates that it's on one set, -1 the other set. Okay, so that's my optimization variable. Now I want to, what is the objective function in this case? It's the cut, right? So one particular labeling defines a cut, and that's what I want to maximize over. Now the question is, can I get a nice expression for the cut? Yeah. Norm of x is what will norm of x be equal to? No, for this, take any x in this set. What will norm of x? I claim that norm of x is always going to be the same for all x in this particular set. Okay, very good. So you, of course, you will need to use the adjacency matrix because that is what specifies the graph. Okay, so now let's try to think about that. What is, we have f of x. Basically, what we want to do, we want to count the number of edges going from one side to the other side. Correct? Okay. So now, okay, so let's try to.
The particular set V1.
Okay.
Should not have.
What do you mean?
This number of edges between.
Again, you're jumping too far. We don't want to optimize anything yet, right? Our goal is to just understand what the objective function is, right? So let's first define the objective function. Okay, so let's, even before I go to the optimization variable, let's try to think about how to count the number of edges going from one side to another, right? So basically what do you need to do? You take a vertex in, say, V1. So I've split the vertex set into V1 and V2. I take a vertex in V1 and I need to find the number of edges that go to elements in V2. Right? So for a given V1, let's say I is in V1. I is in V1. Take any I in V1. What is the number of edges crossing over to V2 in terms of the adjacency matrix? Okay, so right now, even before going to x, so I've given you V1 and V2. Okay, two sets. Okay, we'll get to that. But basically, the number of edges going from I to V2 is basically summation overall j in V2 of Aij. Do you all agree? That's fine, right? And what is the total number of edges going from V1 to V2? Very good. So it's sum overall I in V1, sum overall j in V2, Aij. Okay, so this is fine. Great. Now let's try to write this in terms of the optimization variable x.
for I equal to 1 to n, j equal to 1 to n, aij into
Okay, so you're saying I equal to 1 to n, summation j equal to 1 to n, aij
not equal to ij. They're distinct with alpha.
Okay. Okay, so you want whatever, there's an indicator whether xi equal to xj, right? Okay, that's correct, but can we somehow simplify this? I want to use x itself somehow. I don't want this sort of complicated looking function. Okay, so let's try to do it step by step. Let me look at the following quantity. Okay, I'll take summation I equal to 1 to n, summation j equal to 1 to n, aij xi xj. Okay, let's take this. Let's look at this particular quantity over here. So what does this give me?
There's no there's a cut between the I and the J vertex.
Sorry.
So you get one if both I and J are.
Okay, so let's look at xi xj. It gives me xi xj is 1 if I and j are on the same side, and it's equal to -1 if they're on different sides. That's fine, right? Okay, yeah, so this doesn't exactly give us what we want, but now we can sort of split it into two things. There are terms which have a positive sign, correct? And these, so let's keep that aside. All the terms with the negative sign are basically what we are interested in somehow. You agree? Okay, so now let's look at the terms with the positive sign. Yeah.
So instead, could we write mod of xi minus?
Mod of xi minus xj. Okay, yeah, so that's
If I and j are on the same side, that would be 0.
correct.
That would be just a maximization.
Correct. So that's certainly a valid way to do this. So you can certainly say that this is xaij mod of xi minus xj. Right? Okay. Is this enough? So you need a scaling factor, right?
Yeah.
Yeah.
It's fine.
So it's fine. Yeah. Maximizing this is equivalent to maximizing the cut. But if you wanted to exactly find the max cut, it would be half. Right? That's a valid way to do this. But I claim that you can simplify it. So this is in terms of a mod, right? Which is not always nice. You can actually write it in the form of something times xi times xj in the form of sort of a matrix equation.
I want to remove the mod, why not square it?
You can square it. Certainly you can do that. But what I want to do is only keep the xi xj terms. Effectively, what I'm going to do is the same, right? It's going to be similar to what you have just proposed. So maybe let us do it along those lines, right? So maximizing this, so this is the same as xi minus xj the whole square. Now this is a scaling factor that is required, right? And what is that going to be? 1/4, right?
So there would be double counting.
Why?
Because each edge will be twice in that.
Each edge will be coming.
Twice in that system.
Correct.
We should
Correct.
include it
Okay, so how many times are you counting things? A particular edge
twice.
twice. So it is going to be this times.
Another.
Okay. Okay. So fine. This is going to be the objective function. Correct. So this gives the value of the cut. Does everyone agree with that? Okay, when xi is not equal to xj, basically we want to count a 1 if xi is not equal to xj, right? And whenever xi is not equal to xj, xi minus xj is what? It's either 2 or minus 2. And when you square, you get a 4. Okay? Fine. So it's some constant times summation I equal to 1 to n, summation j equal to 1 to n, aij, xi minus xj the whole square. I'll expand this out. Xi square plus xj square minus 2 xi xj. But what is xi square and what is xj square going to be equal to? Right? It's always, so xi square is always 1 because xi is either plus 1 or minus 1, and the same holds for xj. Correct? Okay, so this is 1/8 summation I equal to 1 to n, summation j equal to 1 to n, aij times 2, let's say 2 into 1 minus xi xj. Okay, this is summation 1/8. What I'll do is I'll split these two terms in the following way. There's a reason why I'm trying to do this. I equal to 1 to n of, let me put it in the following way, 2 aij times j equal to 1 to n aij minus summation j equal to 1 to n of aij xi xj. Okay, I've done nothing but just split those terms. So for a given I, what is summation j equal to 1 to n aij going to be equal to? Yeah? Correct. So it's a total number of edges which are leaving vertex I. Correct? And this is called the degree of vertex I. So this is 1/8 summation I equal to 1 to n. I can take the 2 outside, which gives me a 1/4 summation I equal to 1 to n di, where di is the degree of vertex I, minus summation j equal to 1 to n aij xi xj. Okay, so now I'm going to define a new matrix, which is at least in CS terminology, it's called the graph Laplacian. Right, this matrix L is basically a diagonal matrix with the degrees minus the adjacency matrix A. Okay, it may appear weird why I'm doing all of this, but as you will see, the final objective function will have a nice form if I do this particular thing. Okay, my claim is that this quantity will be just 1/4 x transpose Lx. So let's look at this particular quantity. What is the ijth entry of, or what is this equal to? Can you give an expression in terms of Lij? In terms of Lij, xi and xj, what will this be equal to?
Lij into xi bits.
Lij into xi into xj. Does everyone agree? So if you look at, say, the ith entry of L times x, what will that be equal to? Right, so L times x is going to be a vector of length n, and it's basically the ith row of L multiplied with x. Correct? So what will that be equal to? It is summation overall j Lij xj. Right? So this is the ith entry of Lx. Let me call it, say, yi. And what is x transpose y equal to? It's summation overall I xi yi. Right? So this is just summation overall I xi times summation j equal to 1 to n Lij xj. Correct? Does everyone agree? Okay, but what is Lij equal to in terms of D and A? So D is a diagonal matrix. So if I is not equal to J, then Lij is just minus Aij. Correct? If I is equal to J, then what is Lij equal to? It's equal to Di, right? The degree of the ith vertex. This is exactly what we have over here. Correct? We all agree? Fine. Okay. So I have this particular quantity, right? It's a quadratic form. It's x transpose L times x. And this is equal to this particular quantity. You agree with that point? Correct? Now, but what is Lij equal to? Right? If I is not equal to j, then Lij is basically Ai minus Aij. That is fine. Right? So this, but if Lij equal to, if I is equal to j, then what is Lij equal to? But it's Di minus Aii. Correct? You agree with that? But what is Aii equal to? It's always 0, because we're assuming that there are no self loops. That's an assumption that we're making. Right? So it's always equal to Di. But when I equal to j, what is xi times xj? Xi into xi, which is always equal to 1. Right? So if you take all the entries corresponding to I equal to j, you basically get summation I equal to 1 to n di. And when I is not equal to j, you get these I equal to 1 to n Aij xi xj. Right? So of course it may seem a lot more cumbersome, but the advantage of this particular formulation is that it has this nice quadratic form. right? So it's X transpose times L times X for some matrix L. So the goal would be to maximize X transpose LX over all possible vectors X, which only have +1, -1 entries, right? That's a constraint that you need to pose. So the goal is to find X star, which is argmax over all possible +1, -1 vectors of X transpose L times X. Now this looks like a very nice problem, possibly easy to solve because it's a quadratic form, involves just a matrix multiplication, and you're maximizing over all possible vectors X. You only have a finite number of them, so great, right? So it's much simpler. It at least appears to be much simpler than the previous problems you see, because the space of optimization is finite. You only have 2 to the n possible vectors, whereas in the previous case we had it was over a continuous space, right? It was over Rn, right? But in fact, it turns out that this is computationally a very hard problem. In fact, solving this exactly is known to be NP hard, right? Because after all, we're trying to solve all of these problems when you have a huge number of variables. You're not looking at trying to solve these problems when you have 1 variable or 10 variable or 100 variables. Typically, you have thousands or millions of variables. And in that regime, this problem becomes extremely hard to solve. All right. So this is an example of what is called a combinatorial optimization problem, where you're optimizing over a finite number of, where your optimization variable comes from some finite set, right? Typically, it involves some binary formulation. So in this case, each entry is either +1 or -1. It's only binary, right? And the number of variables is very, very large. All right, and most of these problems are computationally very hard. Okay, so it may seem that our convex optimization techniques are not very helpful here, right? Because after all, the space of optimization is discrete, whereas typically when we're studying convex optimization problems, we're looking at continuous parameter optimization. But then it turns out that you can try to get approximate solutions to this particular problem, right? In fact, whenever you have a combinatorial optimization problem, the best line of approach is to approximate this as a continuous optimization problem, and then maybe do some thresholding in the end if required. All right. So there are many different formulations. So that's what is known as a relaxation, right? You have this optimization problem that you want to solve. You know that it's extremely hard, extremely complicated to solve this particular problem. So I'll try to solve an easier problem, which hopefully gives me a solution which is close to the solution for this problem, right? So that's called a relaxation. All right, and there are different relaxations that one can consider. Okay, so one common relaxation. So there are different ways of relaxing. So firstly, you relax the constraints, right? So right now what I'm saying is that the constraints are such that xi is either +1 or -1, and this is my objective function. There are different things that you can relax over here. Either I can relax my objective function itself, or I can relax the set of constraints. Correct? So typically, if I have a combinatorial optimization problem, I'll try to relax it by saying that, okay, I don't necessarily want the constraints to be +1 or -1. I say they can take any value, any real number between +1 and -1. That's a relaxation. It's not guaranteed to give me the same solution as this, right? But fine, that's the best that I can hope for, correct? Also, I can potentially relax the objective function itself. I use some other function, right? So I can relax the constraints or the function. Typically, this is called a surrogate function. So I replace the objective function with a new objective function, which is hopefully easier to optimize over. Now, depending on the surrogate function and depending on how you relax the constraints, it will either be a good approximation or a bad approximation. There's no guarantees per se. It's up to you to show that for this class of functions, you can relax things in a certain way so as to get a good approximation. All right. And there are different relaxations known for this particular problem. It turns out that, of course, you cannot compute the max cut exactly, but then suppose I want to know what is the approximate max cut, then there are different relaxations. One way to relax this is to formulate this in terms of a linear program. You can go through the notes that I've uploaded, so that has more details. And another way is, but it turns out that that's not so great. That was the best known till quite recently, but it turns out that there's a better relaxation which gives a better approximation factor. Okay, so these are techniques. So when you have any complicated problem to solve, any complicated optimization problem to solve, the first approach is, well, can you solve it exactly? If you can't solve it exactly, then can you solve it approximately? How do you solve it approximately? There are different techniques. So one is a relaxation. Right? That's the most common technique that is used. Right? Any questions?
One question is that if we apply some relaxations, the
Yep.
problem may not actually, like the form that we get after relaxing may not even correspond to the problem itself, right?
Correct. Correct. That's true. So that is why you have to be very careful when relaxing. You have to show that somehow you have to prove that your relaxation is going to be close to the minimizer for your relaxed problem, or maximizer for the relaxed problem is going to be the same or close to the optimizer for the given problem. Right? Of course, one way to do it is just use a heuristic. For a huge bunch of problems, numerically you find that this is close enough to this, therefore that's good enough. But then you can also, in many cases, you can prove that the relaxation is close to the actual optimizer. And that's not easy. It's in general going to be hard. Any other questions? Okay. So now we've seen a bunch of different examples, how one can formulate problems, different kinds of optimization problems, right? We started off with a nice, simple looking quadratic optimization problem, the least squares problem, and then you can impose constraints. We also saw sort of combinatorial optimization problems, non-convex problems, and so on. And we'll go through more such examples as we go through the course. Right? But before we take on the challenging problems, let's first recall the simple techniques that you've already learned, because that gives a lot of intuition. Right? So let's just take optimization over a single variable. Right? Basic calculus, you would have seen this in your high school. Right? So let's do it systematically. Let us define terms. Let's try to see what is possible and what is not possible in the single variable case. Right? So the class of functions that we are going to try to optimize over is this class of convex functions. Right? So we say that a function from R to R, the set of real numbers to the set of real numbers, is convex if we have the following, if for all x1 and x2, you take any two real numbers and you take any number alpha between 0 and 1, we have f of alpha x1 plus 1 minus alpha x2 is always going to be less than or equal to alpha times f of x1 plus 1 minus alpha f of x2. All right. So this is the mathematical definition of a convex function. Another related definition is that if, so this is less than or equal to, if this equality holds only for alpha equal to 0 and alpha equal to 1, then we call it strongly convex. If equality above holds only for alpha equal to 0 and 1, then we say it is strongly convex. All right. And similarly, we'll say that a function is concave if minus f is convex. All right, so let's look at this definition a little more carefully. What does it mean? What is the geometric interpretation? Right, so let me take, so typically when you think of a convex function, what should it look like? Yeah, so something like parabolic, like a bowl shaped kind of thing, right? So visually, this is what a convex function would look like. Now, what does the definition say? The definition says that if I take any x1 and x2 and any alpha between 0 and 1, so let's pick an x1. So this is y, this is x. Let me pick 2 points. Let's say this is my x1 and this is my x2. So at this point I have, so this is y equal to f of x1 and this point is going to be y equal to f of x2. Right? Now if I take alpha x1 plus 1 minus alpha x2, where is this going to lie? If I take alpha between 0 and 1. Yeah? It's going to be some point between x1 and x2. Everyone agrees? So depending on where what value of alpha I choose, some point in between is going to be, let me call this x, and this is equal to, maybe let me call x bar, alpha x1 plus 1 minus alpha x2. The value of f at this point is basically f of alpha x1 plus 1 minus alpha x2. Great. So that is what I have on the left hand side. Right? This is the y value at this particular point is f of alpha x1 plus 1 minus alpha x2, which is what I have on the left hand side of my definition. What about the right hand side of my definition? What is alpha f of x1 plus 1 minus alpha f of x2? Where is it going to lie? Right. So that is basically going to be on the line joining f of x1 and f of x2. Right. So basically what this definition says is that if I take any 2 points, the function is convex if if the following holds, I take any 2 points on the curve, the straight line joining these 2 points should always be above the curve. Right? So that's the definition of a convex function. Similarly, it is concave if I take the straight line joining any 2 points, the straight line should always be below the curve. Right? That's the geometric definition of a convex or a concave function. And strongly convex if the curve is strictly below the straight line. Right? So, for example, if I took the following function, right? So take the following function. This is f of x, which is 0 if x is, say, less than or equal to 0, and it's equal to x if x is greater than 0. All right. Is this function convex?
Yes.
Yes. Anyone saying no? So you take any 2 points, pick any 2 points. There are not a lot of choices. If you pick 1 point on the left of 0 and 1 point on the right of 0, and you draw a straight line between these two, it's always going to be above the curve, right? If I pick a point, 2 points on the left hand side of 0, then the straight line basically coincides with the curve, and in any case the curve is not above the straight line, so it's still convex. But this is not an example of a strongly convex function, right? Because in some cases the straight line coincides with the curve. It's strongly convex only if the curve is always going to be below the straight line. All right? Sorry? Okay, so the function is strongly convex if the curve is always going to be strictly below the straight line. The only points where the curve and the straight line intersect are at the endpoints. All right? If that happens, then if this happens for every pair of points, then it is strongly convex. So suppose I took f of x equal to x squared. Is this convex? Yeah, f of x equal to x squared, it's parabola, it's strongly, it is convex. Is it strongly convex? It is, right? Because no matter which pair of points you take, the straight line is always going to be strictly above the curve. Right? Everyone's fine with this? Great. So was this the definition of convex functions that you studied in your high school? Yes? No? Did you see this particular definition? Yes? No? Okay, yes. So how do you test for a convex function? Yeah? Okay, can someone loud? Okay, so f so a function f from R to R whose f double prime of x. So let's take any function f for which the second derivative exists at all points. So this is convex if and only if f the double derivative is greater than or equal to 0 for all x. All right, and it is strongly convex if the second derivative is strictly greater than 0 for all x. Okay. So have you seen a proof of this particular statement? Yeah. Has anyone seen a proof of this statement? Okay, great. So let's try to prove it. Okay. Now, there are two different statements that we need to prove, right? So first, if the second derivative exists and it is convex, then we have to prove that the second derivative is always greater than or equal to 0. That's one part. The other part is if the second derivative is always greater than or equal to 0, then it is convex, right? So that's why it's an if and only if statement. The implication goes on both sides, right? So let's try to prove one way first. The first thing is if the second derivative is greater than or equal to 0 for all x, then f is convex. Right, so we'll use some basic calculus for proving both sides, of course. So let's see what should happen in the case of a convex function, right? So if the second derivative is greater than or equal to 0, what can you say, right? What can you say about the slope at, how does the slope vary with x? Right, so if the second derivative is greater than or equal to 0, then all of you agree that the slope is always, it's not necessarily increasing, but it's non-decreasing. Right, if I take any point x1 and take any point x2, where x2 is greater than or equal to x1, then the derivative at x2 is going to be greater than or equal to the derivative at x1. Okay, just using this, our goal is to show that f is convex, right? That's the only property that we can use.
It's the portion of the parabola where it is coming.
Okay, so that's the question is like this, right? The part where x is less than 0, right? Again, the claim is what? We're only making claims about the derivative and the second derivative. So at this point, what is the derivative going to be equal to? If I take any x, right? F of x is x squared. What is the derivative at x of x squared? It's 2x, right? So at this point, to the left of 0, it's going to be 2x, right? As you move to the right, the value of x increases, right? So here the slope is negative, but it becomes less negative as you go to the right. So pictorially, if you had to draw the tangent here would have smaller slope, it would be more negative, but as you go closer to 0, the tangent is less negative, right? Yeah. Of course, the absolute value of the slope is a different story. We're just talking about the slope, right? Okay. So to prove that f is convex, what do we have to do? We have to show that f of x1, so you take any x1, x2, take any x1, comma x2, and some alpha between 0 and 1. We have to show that f of alpha x1 plus 1 minus alpha x2 is less than or equal to alpha times f of x1 plus 1 minus alpha f of x2. This is something that we have to show, right? So let me do the following. I'll take the right hand side minus the left hand side. Alpha f of x1 plus 1 minus alpha f of x2 minus f of alpha x1 plus 1 minus alpha x2. Okay, it's also helpful to think about it visually as we go along. So what am I doing? I'm taking this curve, I'm taking these 2 points x1 x2 and the corresponding f of x1 and f of x2. I'm picking some point in between, which is alpha x1 plus 1 minus alpha x2. My goal is to show that the straight line is strictly above this particular point. Okay, I'll rewrite this in the following way. So I'll say this is equal to alpha times f of x1 minus, just for convenience, I'll call this x. Okay, so x is equal to alpha x1 plus 1 minus alpha x2. This is f of x1 minus f of x plus 1 minus alpha times f of x2 minus f of x, right? Because I can write f of x as f of x times alpha plus 1 minus alpha, right? And I've just split the two. Everything's fine? All right. So I have this f of x1, I have f of x, I have f of x2, f of x. So these are the 3 points that I'm looking at. Okay. Now the only property that I know about f is that the derivative is always increasing, right? So can I somehow get the derivative from these particular terms? Sorry, what?
You can use first principle derivative.
How?
Derivative at a point is defined as,
Okay.
let's say it's infinitesimally not a,
I'm not taking anything infinite. It's very small. It is an arbitrary. Yeah, you're right in the basic idea, but exactly which property are you going to use? Which differentiation? There's no delta or anything, right? So I want x1, x. I want everything in terms of the points x1, x, x2, and x.
Multiply and divide by 10.
Sorry, which one? You want to multiply and divide by? F of x. Okay, how does that help?
first thing we can multiply by x1 minus.
Okay, so this is alpha times x1 minus x times f of x1 minus f of x by x1 minus x plus 1 minus alpha times x2 minus x times f of x2 minus f of x by x2 minus x. You're right. So I want to somehow replace these two by some derivatives. Yeah, exactly. So you use the mean value theorem. So what does the mean value theorem say? Yeah, so this quantity is equal to what? Correct. So this is equal to, by the mean value theorem, this is equal to alpha times x1 minus x times some f of, let's say, beta 1, where beta 1 is strictly between x1 and x, plus 1 minus alpha times x2 minus x times f of beta 2, where beta 2 lies strictly between sorry, f prime, the derivative f prime of beta 2, where beta 2 lies strictly between x2 and x. So basically, what am I doing over here? I have this straight line joining these 2 points. What I've done is x1, x2, and sorry, this is x1, x, and x2. Instead of looking at this straight line, I'm looking at these 2 straight lines, and I know that there is some point in between over here which has the same slope as this straight line, and there's some point in between over here which has the same slope as this particular straight line, where beta 1 is between x1 and x, and beta 2 is between x and x2. All right. Okay, so now we're almost done. Let's just expand x. Right, so this is alpha times x1 minus, what is x equal to? It is alpha x1 plus minus 1 minus alpha x2 times f prime of beta 1 plus 1 minus alpha times x2 minus alpha x1 minus 1 minus alpha x2 f prime of the derivative of f at beta 2. What is this equal to? If I simplify this, what do I get? It's going to be 1 minus alpha times x1 minus x2, or if I want to write it a little differently, it's going to be minus of x2 minus x1 times f prime of beta 1 plus 1 minus alpha times, what is this going to simplify to? Yeah, it's going to be alpha times x2 minus x1 times f prime of beta 2. Okay, so this is alpha. I can take all the common terms out. Alpha times 1 minus alpha times x2 minus x1 times f prime of beta 2 minus f prime of beta 1. Okay, so now let's make use of what we know. So alpha, 1 minus alpha are both non-negative. x2 is strictly greater than x1. We've always taken it to the right. So this quantity is non-negative. What about f prime of beta 2 minus f prime of beta 1? This is also at least non-negative, because beta 2 is strictly greater than beta 1, and we know that the second derivative is strictly positive, is non-negative. So this whole term is greater than or equal to 0. And what did we start out with? We had this particular quantity, right? So which means that alpha f of x1 plus 1 minus alpha f of x2 is greater than or equal to f of alpha x1 plus 1 minus alpha x2. All right, so hence the function is convex. All right, just a quick recap. So what did we do? We took the following expression. So we knew that the second derivative is greater than or equal to 0, which meant that the slope is always increasing. So we took 3 points, x1, x2, and some point x in between. Essentially, our goal was to show that this straight line is always above this particular curve, right? So instead of doing this, we split this segment into two different segments. One going from x1 to x, the other going from x to x2. In other words, we split this particular function, this particular term, into two parts, alpha times this plus 1 minus alpha times this. And using the mean value theorem, we showed that overall the quantity was greater than or equal to 0, right? So effectively, we replace these terms by two different terms in terms of the derivative of f at two distinct points. Correct? And therefore, the function is convex. Any questions? All right. So let's stop here. We're out of time. So in the next class, we'll see how to prove the reverse way. Right? If the function is convex, then how do you argue that the second derivative is always non-negative?